Chemistry in Context, G.C. Hill, J.S. Holman, Low Price Edition. Chemistry in Context, the English Language Society, and Nancy Graham, C. Hill, Deputy Headmaster, Dr. Chalona's Grammar School, Amazon, formerly Head of Science Special Grammar, Jonas Holman, M.A. Canterbury, Head of Science, Watford Grammar School. Chain reactions, atomic bombs, and nuclear reactors. All of the neutrons released during the fission of U-235 are capable of splitting another uranium nucleus. Figure 6.4 shows how an exploding chain reaction can occur during a uranium fission. N plus 235 uranium N plus 235 uranium N plus 235 uranium N plus 235 uranium, splitting further into 3 each. N plus 235 uranium N plus 235 uranium N plus 235 uranium N plus 235 uranium ions, and all splitting in threes into further into plus 235 uranium ions. This is a simplified diagram to illustrate an exploding chain reaction during uranium fission. One reaction releases 3 neutrons, 3 neutrons release 9, and then 27, then 81, and then 243, etc. Provided the chain can be built up rapidly and completely, there is an enormous release of energy, an atomic bomb. These will only occur if the sample of uranium-235 is large enough. If it is too small, the secondary neutrons will escape from the sample because they have caused further fissions and the chain reaction will be broken. Figure 65. In brackets A close A brackets A. Thus, a small piece of uranium-235 is quite safe, but a large piece within which the secondary neutrons cause further fissions before escaping may explode. A small piece of uranium-235 is quite safe, but a larger piece within which the secondary neutrons cause further fissions before escaping may explode. This is therefore a critical size below which uranium-235 is safe, but above which it may explode. If in an atomic bomb 2 pieces of pure uranium-235 or Pu-239 each below the critical size are brought together to form one piece larger than the critical size, fission of uranium-235 or Pu-239 then proceeds in an uncontrollable manner as an exploding chain reaction. Why must the uranium-235 used in an atomic bomb be pure? How can the fission of U-235 be controlled in an atomic reactor so that the energy is converted into electricity or heat? Neutron absorbing rods, boron or cadmium, hot gas in, outhouse gas out, graphite moderator, uranium rod, cold gas, thick concrete shield. Such figure 6.6 shows a diagram of the commonest type of nuclear reactors similar to that at Calder Hall. The atomic pile consists of rods of natural uranium inserted in channels surrounded by blocks of graphite. The neutrons resulting from the fission of U-235 are slowed down but not absorbed by the collisions with carbon atoms in the graphite. This ensures that as many second neutrons as possible cause further fission of U-235 atoms before escaping from the pile or before captured by the more plentiful U-238 atoms. The temperature of the pile can be controlled by movable rods of boron or cadmium which absorb neutrons. The deeper these rods are inserted, the more neutrons are absorbed and the fewer fissions can take place. By carefully adjusting the position of these rods, a controlled chain reaction can be obtained with a steady and continuous production of energy. The heat produced during the fission processes is removed by a stream of circulating carbon dioxide. The hot gas can be used to make steam and then drive a turbine. Why must the uranium rods be stored well apart before use in the reactor? Why do fewer fissions occur when the rods are removed during the pile, even though they are the same distance apart? Why is it necessary to surround the pile with a thick concrete shield? Besides liberating energy, the atomic reactor also produces plutonium as a result of the neutron bombardment of U-238. the plutonium can be separated from the uranium and used as the atomic fuel in the nuclear reactors, such as the one at Donray. Since plutonium requires faster neutrons for fission than U-235, no graphite moderator is necessary. The central core plutonium is surrounded by natural uranium, which captures any neutrons escaping from the central core and becomes converted to plutonium. By careful design and control, it is possible to produce more plutonium in the surrounding uranium than is used in the central core. So consequently, this type of reactor is called the fast fission breeder reactor, since it uses fast neutrons and breeds plutonium from uranium. Although such reactors produce more plutonium than they use, we are not getting something for nothing. There is a consideration for the laws of conservation of matter and energy, since uranium and plutonium have been converted into more plutonium. Check this yourself by using the last set of equations. The 10n plus 238, 92u to 239, 92u, 239, 92u, 239, 92, 293 Np plutonium plus 0 minus 1 electron, 239 and 3 Np, 299 4 Pu plus 0 and 1 minus U electron. The energy from disintegrating the plutonium that destroyed Nagasaki has been tamed. For more than 20 years, nuclear scientists have been trying to harness plutonium as the fuel for the future in the fast breeder reactors. Many people, however, consider the dangers in using plutonium to create atom bombs in the hands of terrorists or unscrupulous governments might prove catastrophic. Atom bombs in the hands of terrorists or unscrupulous governments might prove catastrophic. Atom bombs in the hands of terrorists or unscrupulous governments might prove catastrophic. On the other hand, the benefits of plutonium seem irresistible: cheap, abundant electricity for hundreds of years, will our descendants cast or places for the legacy of plutonium. Using radioactive isotopes, the structure of DNA within the genes of animals and plants can be changed by radiation. For reasons which are not yet clear, cancer cells are more susceptible than normal cells to destruction by radiation. Because of this radiation, gamma rays can be used in the treatment of cancer. Penetrating gamma radiation from cobalt 6027 cobalt is used in treating inaccessible growths, whereas superficial cancer such as skin cancer can be treated by less penetrating radiation from 3215P or 9038 SR in plastic sheets strapped on the affected area. Studying metabolic pathways, radioactive isotopes can be used to trace the uptake and metabolism of various elements by animals and plants. For example, the uptake of phosphate and the metabolism of phosphorus by plants that can be studied using a fertilizer containing 30-15P. Radioactive tracer studies using 14-6C have helped in the elucidation of photosynthesis and protein synthesis. 13154I has been used in the diagnosis of treatments of thyroid disease and in the research of thyroid gland functioning. Thickness and gauges and empty packet detectors. The radiation passing through a material decreases as the material gets thicker. Thus, the amount of penetrating beta or gamma radiation can be used to estimate the thickness of various materials such as paper, metal, or plastic. The advantage of using radiation for measuring the thickness of materials is that there is no touching, marking, or tearing of the article concerned. Thus, radiation thickness gauges can be used to control the thickness of sheet steel emerging from a high-speed rolling mill. Beta rays can be used for material thickness up to 0.2 centimeters of steel, whilst gamma rays can be used with steel of up to 10 centimeters thick. A similar use of radioactive isotopes is made in level gauges and empty packet detectors. The level of liquid in a closed level can be found by placing a source on one side of the container and the detector on the other. A sudden increase in the detected radiation when source and detector are moved down the vessel simultaneously shows the level of liquid within the vessel. Level gauges of this type are used to measure the amount of liquid in fire extinguishers and gas cylinders. In a similar fashion, empty packet detectors can be used to reject empty or insufficiently filled packets of biscuits or cigarettes. Summary: radioactivity results from the spontaneous disintegration of nucleus. Naturally occurring elements which undergo radioactive decay emit alpha particles, 4-2 hydrogen and ions, beta particles, electrons, and gamma rays, electromagnetic radiation. Gamma radiation is far from penetrating than alpha, is far more penetrating than alpha and beta radiation. It cannot penetrate through thick metal sheets and is responsible for most of the damage caused by the disintegration of radioactive substances. The half-life of radioactive isotopes is the time taken for the mass or concentration of the isotope or for its rate of decay to fall. Half of its initial value. The half is virtually unaffected by external conditions and can be used as a measure of its relative stability. The N-stroke P ratio of four stable isotopes lies within a very restricted range for any given atomic number. Isotopes which are unstable due to an excess of protons over neutrons N over P less than stable value can increase the stability by alpha particle emission. Isotopes which are unstable due to an excess of neutrons over protons N over P over stable value can increase the stability by beta particle emission. Atomic nuclear fission is the disintegration of an isotope into two large fragments. Chemical reactions involve electrons from the outer parts of atoms, whereas the nuclear reactions involve protons and neutrons in the nucleus. Manufacture of nitric acid from ammonia involves three stages: catalytic oxidation of ammonia to nitrogen oxide, nitrogen 4 nitrogen hydride grams plus 5 O2 grams irreversible changes to 4 nitrogen oxide grams plus 6 hydrogen oxide. That means water appears grams with temperature changes of minus 950 kilojoules. And then the second step is the oxidation of nitrogen oxide to nitrogen dioxide with 2 nitrogen oxide plus O2, both gases, to give 2 nitrogen dioxide gas with the enthalpy changes of minus 114 kilojoules. The third reaction is the reaction of nitrogen dioxide with water to form nitric acid with 3 nitrogen oxide gas plus 2 hydrogen oxide liquid plus 2 nitric acid aqueous to react to form 2 nitric acid aqueous plus 2 nitrogen oxide with enthalpy changes of minus 117 kilojoules. Closer look at stage 1 above. What conditions of temperature and pressure will give the maximum yield of nitrogen oxide at equilibrium? In practice, the first stage is carried out by passing dry ammonia and air at 7 atmosphere over platinum gauze catalyst at 900 degrees. Explain how the conditions used in the process differ from those predicted in your answer to the last questions. Product gases are cooled to 5 degrees and then mixed with more air so that the nitrogen oxide is immediately oxidized to red brown nitrogen dioxide. Nitrogen oxide to nitrogen oxide plus oxygen gas, both gases to nitrogen oxide gas plus 2 oxygen gases react to form 2 nitrogen oxide gases, 2 nitrogen oxide ions, and to nitrogen oxide ion compound, to nitrogen oxide to nitrogen oxide ion compound reacts with an oxygen compound, gaseous compound, to form two nitrogen oxide gaseous compound. In the third stage, the nitrogen dioxide reacts with water with large absorption towers designed to ensure thorough mixing of the ascending gases and the descending solution. The final product contains about 60% nitric V acid, and more concentrated acids can be obtained by distilling the 60% solution with concentrated sulfuric acid.